two-part series. Today, we're going to be discussing transforming neonatal care with artificial intelligence, and our presenter will be Dr. George El-Ferzli. He completed both his pediatric residency training and fellowship training in neonatology at the University of Alabama, and he currently serves as the Director of Innovation in the Division of Neonatology at Nationwide Children's Hospital, where he's helping develop a very strong focus on creating cutting-edge technology and artificial intelligence. Let's please welcome Dr. George El-Ferzli. And I would just like to remind everybody to keep your mics muted and to direct any questions that you have to Dr. El-Ferzli to the chat box, and I'll consolidate any questions towards the end of the presentation. Thank you.
Hi, everyone. Thank you for inviting me. It's a pleasure to talk to you a little bit about AI in neonatology. So the talk will be about empowering neonatal care, the frontier of artificial intelligence in neonatology. It's going to be a broad topic. It's mostly educational without too much details. First, we'll talk about a historical perspective with definitions and applications. Second, we'll move into understanding the applications of AI in neonatology. I'm going to give you very specific case studies that we are doing at NCH. And then what are future prospects, challenges, and ethical considerations. So really, I think every time I give this talk, it is talking to clinicians, especially when they are in training. And it's like the same as any topic in research. It is being too much mystified. So really, the aim of this talk is not to give you details, but to demystify the topic of AI, and hopefully you get to be involved in research and interested in reading about it. So as you can see in here, this is the cognitive and AI systems. This is the market revenue. And from 2015 to 2024, you can see the revenue was $5 billion and became $110 billion. So this is more than 20 times increase in less than 10 years. So this is a huge increase in the revenue worldwide. If you take the market size, it is from 2022, which is $450 billion. It is expected to be in 2032, $2.5 trillion, which is also a 5-fold increase within 10 years. Again, this is the market size, which is a huge. If we look at the current and a little bit in the future of the AI market, AI in healthcare market size, so the other one was just AI in general. You can see in 2021, it was $11 billion, and it's expected to become $187 billion. You can see that we are doubling every 2 years. It's also a huge increase in the market size. And again, this is just for healthcare. You can see that in 2021, it was in 2020, it was 4.5 billion. And then it's been going up by 2.5 billion, expected to become 45 billion in 2024, with continued increase of 45% until reach in 2026, $150 billion. So the question is, AI a hype, you know, and you can see here, part of it might be, if you look at the left side, probably this is where we are right now. It is interesting, but probably more realistic. Are we going to move to the next step where it is truly very futuristic? And as you can see here, this image was made by hot mods from ChatGPT. You can write it, and then it can transform your writing into a picture. So I'm going to talk about an overview of artificial intelligence first. So what is AI definition? It is the ability of a digital computer or computer-controlled robot to perform tasks commonly associated with intelligent beings. Basically, it's pretty simple. So we assume we are intelligent beings, and the computer or a robot has to perform the same task as we do or better. So we think that AI is something new because we've been talking about it mostly for the last 5 to 10 years, but actually it's been going on and talked about for more than 3,000 years. It started with dreams, and some actually of them had some designs for it. So I'm giving here very few examples. The first one was from China about the Yanqi mechanical servant in the 4th century. This was a design. The Greeks were very excited about it. The first one, the first robot was Talos in the 3rd century BC. And this was the first killer robot, if it is exciting for you to know about how robots can be working for us. Then the 1st century, there was a design using also the steam engine, and also it was the first ED in Greece. Another China, it was a robot about a horse. It's called the automated musical Trojan horse. And the Banu Musa brothers, they had published in 830 AD a book that had more than 100 designs of robotic and automatons, really what's used to be called at the time. Time has passed. Lots of that continued throughout, mostly in Europe. But most recently, if we go back to the 1642, it was the first mechanical calculating machine. In 1837, we had the first design of a programmable machine. In 1943, you think of the neural network, that's something which is new. Actually, it goes back to 1943. In 1950, the Turing test, which is a way to test a machine intelligence, started. And the current term of artificial intelligence was coined in 1955. So if we want to go exact, 1955 was the year that we start talking about what we know now about artificial intelligence. And as you go 1995, 1980, 1997, you can see that we're having different chatbots. For example, Eliza, that was the first natural language program, and it was in 1965, although now we talk about ChatGPT and chatbots. So that was 60 years ago. In 1997, it was the first time that a machine can beat somebody, which was at the time in chess, and it was the Deep Blue, and it beat Kasparov, who was the champion in chess. Then the time goes on, we have iRobot in 2002. Then Google had in 2009 the first driving car, and then IBM Watson in 2011 beat the Jeopardy, won Jeopardy, and then you start having personal assistants like Siri and others in 2011, and it goes on. And 2014, we start talking about the GANs. So it seems very exciting, but if you look at this one here without having to go into details, because they are very similar to what I just talked about, from 1966 to 1997, we had AI winter. So it took more than 30 years. Really, people did not talk about it because we had so many false starts. And it's the same what I talk about right now, is you do not want to overpromise and underdeliver. And that's exactly what happened. And recently we had similar problem, but now we are hopefully not going back into this kind of winters. So if we are going to define simply AI, by capabilities, we can see that we can divide them into 3 kinds: the narrow AI or weak AI, or also known as artificial narrow intelligence, the AGI or general AI, which is the artificial general intelligence, and super AI. So this is the what we can call the future of AI, and this is really the current of AI. It's the only type that exists right now. It is trained to perform a single or narrow task, although we think it is a lot, but actually the tasks are very narrow. And it targets a single subset of cognitive abilities and advances. So Siri, Alexa, Watson, ChatGPT, even it is still within artificial narrow intelligence. The general AI, it goes to the next level where you can use previous learnings and skills to accomplish new tasks in different contexts. So it learns from something and apply it to something completely different, which is not the case right now. We teach it on one topic and it performs a great job in the same topic. And then it does not need for human beings to train the underlying models. Actually, it teaches itself. The super AI becomes more of a being and superhuman, if you want, where it would think, reason, learn, make judgment, and possess cognitive abilities. And this is the most important part here, cognitive abilities, and surpass those of human beings. If we go by functionalities, we have what's called the reactive AI, machine AI, and limited memory AI. And these are, again, the only two that we have right now. In the future, people are aiming for theory of mind and the self-aware AI. If you are familiar with it, with the word singularity, this is when we achieve singularity where the machine takes over humanity. At least that's what people are feared of. So for the reactive AI, it has no memory. It is defined to be taught to perform a very specific task. It only works with the presented available data and stems from statistical math. Now here we can move a little bit where we have generative AI, which chat GPT and chatbots and self-driving cars, because they can start, instead here, as you can see, it does not, it has to start with the data and perform a task, but here it can create and generate data, which is different than the reactive part. It is still limited because it is within specific tasks, but it can recall past events and outcomes, which is different than this one that had no memory. Now, for the theory of mind, it would understand the thoughts and emotions of other entities and would infer human motives and reasoning. And when it gets to self-aware, then we would have ability to understand its own internal conditions and traits along with the human emotions. Basically, it becomes superhuman. So if we look what happened over the last 2 decades or so, if we start by assuming that the human performance is really the benchmark, what we're aiming to, and we set it at 0, and then we normalize the performance of AI at the start at -100. So you can see that the handwriting recognition, which started a little bit before 2000, it took from 2000 to 2016 or so to achieve, or if you want to be here, maybe 2012 or so to achieve human performance. You can see that speech recognition also started at the same time. It took the same amount of time to achieve that. You can start seeing that image recognition in 2010 start going faster. And you can see the skyrocketing here in 2016, where reading comprehension and language understanding, they happened so quick. And you can see that it was almost like up all the way. But you can see that ultimately so far where we are now around 2020, we have all these performances or capabilities are at or above the human level of performance. So basically, the goal has been achieved of doing similar or better than the human intelligence. So we are going to have a little bit of learning, very basic learning about AI. I think that a little bit of confusion because most of the time clinicians do not differentiate between the different types. AI really is the big umbrella. And there's somebody who talks about probably cognitive computing, which is even larger, but we can, for the purpose of this talk, we assume that AI is the global umbrella, where programs will have the ability to learn and reason like humans. A subset of that would be machine learning, and you can see that algorithms with the ability to learn without being explicitly programmed. A subset of machine learning will be deep learning, where you have artificial neural networks adapt and learn from large data set. And the data science is really the cross-disciplinary field that seeks to extract meaningful insights from data. So as we will see in a minute, that within that, Gen AI is within the deep learning. So when we're talking about machine learning, again, it is a subset of AI, and deep learning is a subset of machine learning. It all starts with data. So without data, we do not have AI or machine learning. The next level would be data engineering, then data science, visualization, and decision support. And you can see here it's the intersection of these different fields and expertise. You have computer science with math and statistics, business domain expertise, which is healthcare in our case. And you can see you're having traditional software, data analysis, machine learning, and all of this would be data science intersection. So really, if you think about it, AI is not much different than what you already know and have done for years, which is basically statistics, as you know, and some math. So the building block of AI are, first, you start with sample, which is, what relates to a population. Then it is the same where you have descriptive statistics like mean, median, standard deviation, inferential statistics, confidence intervals, hypothesis testing, and then statistical method models like regression models and decision trees. I'm going to show you really most of these you already know, and this is where I'm talking about demystifying. It is not way much different. You can learn it and apply it. So here, if we're going to look at the different math topics which are needed for machine learning, you can see that 35% is linear algebra that you already kind of know and use many times in your research. Then you can have probability theory and statistics that are 25%. So you are already 60% expert in doing machine learning. Then you can have multivariate calculus, and you can see that the algorithm and complexity is only for 15%, and other stuff is 10%. So the vast majority is 75%, and you can learn it and do it. And I think that's the purpose of this talk, is to make you excited and don't be challenged by the concept. Again, it's the same here. We have how to build a data-driven solution. You have 6 steps. One, you start with defining the problem, have a problem statement. Then you collect the data and you formulate it the way to answer your question. You prepare it because it needs data preparation. You have to clean it and prepare it for your algorithm. Then you have to have exploration data analysis, where you explore the data, mine for insights, identify pattern before you jump into doing the machine learning. And you can see the machine learning is really the 5th step. It is the statistical modeling to extract insights, predict, and classify or prescribe. It's the same thing as you do research. You have to have lots of preparations before you jump into doing your research. So it is the 5th step. You get there. And then you have to do dashboarding, tracking of outcomes. And this is when you measure your outcome, and we're going to go into a little bit more details in the next slide. So first you start with data pre-processing. You have to encode, transform, and scale. You have to put in the right shape and form. The next step is you train your model and given whatever data that you have. Then you fine tune it because you can have hyperparameters. The problem with that is that you want to prevent is underfitting and overfitting, because you want your model to be generalizable and not just perfect for your data, because that if it only works on your data, then it is not worth it. Then you test and the performance of your first after you tune it. Then you have to evaluate in real life. So here you go and test it on unseen data. What we call unseen data is you put a test in real world setting, and you see what people are saying. Is it useful? It is not, or because you don't want to implement something that people are not interested in and it's not helpful to you. And then you deploy and you expose the model, you integrate, for example, in your EHR and test it. And then you have to monitor key performance metrics for anomalies, errors, and you keep the cycle going on. It's a continuous improvement. Things are going to change. You're going to have a new data coming in. You have a new technology, so you can adjust and you update your model. So it is a continuous improvement process that will keep going. And that's why monitoring after the deployment is extremely important. So you start with your raw data, then you prepare your data cleaning, you look for missing values. You know how EHR already talks about the noise in the EHR data, inconsistent data, and then we transform so it can be generalizable and normalized. And then you go to the concept of feature engineering. Not every data is important, so you remove what it is not needed and you use feature reduction, and then you do your machine learning. So it's pretty simple. If we are talking about just machine learning, we only have 3 categories how to train a model. The first one is supervised learning, second is unsupervised learning, and third is reinforcement learning. The supervised learning, we're just going to talk a little bit in detail about it, is how you train it. You have to train and label. Unsupervised, it is self-sufficient, and reinforcement, it takes care of itself. So if you think about it, you don't have really many ways of doing machine learning in the most simplistic way. So you have the unsupervised learning, supervised learning, and reinforcement learning. In the unsupervised learning, there are really two categories, which is the dimensionality reduction and clustering. For example, here we talk about meaningful compression, structure discovery, customer segmentation, target marketing. These are not necessarily healthcare, but these are the same concepts. With supervised learning, you have a classification and regression that you already do in many instances. And then in reinforcement, where the machine teaches itself using rewards and punishment. So it will teach itself how to come up with the best algorithm. So again, with the supervised learning, you provide the data, it is labeled, so it has to know what it is looking at, and you have an output which is very specified. And the unsupervised learning, the data is unlabeled, the outputs are not specified, and the machine makes its own prediction. And the reinforcement, the machine learns from its own environment using rewards and errors. Again, the supervised use very specific problems to solve using regression and classification. Here we use clustering and then use reward and to solve the problems. The data is labeled, unlabeled, and there is no predefined data. The supervised needs supervision by an individual. Unsupervised and reinforcement do not need any supervision. So when you're looking for supervised algorithm, again, we talked about this regression or classification. You know already about linear regression. You can use logistic regression or nonlinear regression. And for the classification, you all know about decision tree and naive Bayes or random forest that you've heard about if you've not used them. So basically, many of these techniques can be just from pure statistics. That's why it is not always necessary to jump into doing more complex machine learning analysis. You can use many times, just if you can, by just linear regression or logistic regression to test your data. It can be just enough. Now, when we go into deep learning, it becomes more complex. You can see here that you have really an input layer. This is what you have, and you have these neurons, nodes, and then the machine will teach itself. All of these layers in here are hidden. You don't see what's happening in here, and that can be a problem because it is not clear and you don't know what's happening. So you don't know what the output. You have really no input. If you are a data scientist or researcher, you really do not know what's happening in these layers in here. You start with this one, you know how you start, and you see how it ends, but you don't have much input in here. So there are different types. There are 7 major types. And as you can see in here, these are the mostly used so far until lately we end up having the Gen AI and its other similar types. So you can see what we call the convolutional neural networks, and these are mostly used for vision, computer vision, and image processing. So everything that you see, if you're looking to look for MRI or CT scan or ultrasound and try to teach, you usually use a CNN. Recurrent neural network is the more common use. And there is the long short-term memory networks. These are all different kinds of networks. But again, these are the basic type of deep learning. And lately, we start having the generative AI or generative deep learning. Remember, again, that Gen AI is part of deep learning. An essential element of the Gen AI is what is called really the transformers. And this will determine of how you start, and it teaches itself. So you have the feature learning. So you can start with a sentence, with a word, with a prompt. So now you learn how to use prompt engineering, and that by itself and there will tell you how to get into the in the end where you generate a word, a sentence. Really with Gen AI, what you are starting is adding the machine is learning to predict the next word. It's not much more complex than that, but it is so vast that by itself it starts seeming that it is coming up with text quick, but actually it is just generating one word at a time. And all it is coming from the transformers. So what is AI in academics? You can see here the scholarly production publications on AI. It started in 2010. You can see how over the world here, it started at around 200,000 in 2010, and now it is more than 600,000. You can see this is the world. This is China. China has the most production. United States is next, and then parts of Europe. You can see here the number of AI publications worldwide from 2016 to 2020, and that's in thousands. You can see China has the most. The next most is United States, and then they drop pretty significant. And here you can see the total number of AI publications by year. It starts again, it is pretty impressive increase. If we go by a healthcare specialty and per year from 2019 to 2022, the blue is 2019 and the green is 2022, you can see that radiology has the highest number of publications. The next one is general. Pediatrics falls in here, not too bad. But you can see there's been a marked increase in all the number of publications. For neonates and adults, the red is over the years from 2001 to 2021, the number of citations. You can see pretty significant increase after 2016 or 2015, and the same applies to the adult. I don't think that really we can compare them because, you know, it's much larger population, much larger topics in there, but you can see that both of them had similar increase over the last 10 years. So what are the applications in neonatology? Again, you start with the machine learning and deep learning. With the deep learning, I'm going to start from the bottom a little bit because that's what we talked about, the CNN. You can see that we can look for images, MRI, echocardiograms, ultrasounds, different kind of images, signal data. Probably you've read a lot and heard about it, how you can look at the different parameters by bedside from heart rate, saturation, EEG, EKGs, and then from the EMR, looking for clinical variables, Bailey scores. From machine learning, also it depends what you're looking at, but you can also look at image data. You can look at vital signs, EEG, the same thing, and there have been studies using both. Most of the time, whatever been studied so far has been using machine learning and predictive analytics in AI and neonatology, and there's been a little bit more about deep learning, but not as much. So what have we done so far at NCH? The focus is really on what we call P4 medicine, which is a holistic approach to patient care. We focus on, again, the P4. 1 stands for predictive, 2 is preventative, 3 is participatory, and 4 is personalized. And this is the whole idea, is you need to predict who is going to get sick with the highest probability, most likely, and how you can help prevent the disease, or you can help prevent a significant illness if you cannot prevent the disease itself. With that, we need to have patient and families participation, and this is how we'll end up having a personalized care for that specific individual. So all of the project that we focus on is to achieve these 4 Ps, and you will see in a minute how we are looking into that. So we're having an integrative approach to innovation. We focus on, again, not on any individual topic in here. They are all integrated in all our topics. So we have research, QI, clinical, operations, and DEI. And again, in all our projects, we have them all integrated within that. Some of them would be heavier on one aspect versus the other, but basically they have to have these 5 fields. So you can see that also we focus on education and entrepreneurship, on outcomes and customer experience. We say customer because it's not just the patient, it is patient and healthcare providers. So how we are looking into data-driven solutions, first we have level 1, which is data platform, level 2, data science and analytics, level 3 is dashboards. And from these 3 levels, we can have insights. So for the level 1 project, it's what we call interoperability and connectivity. Remember that we need as much data as we could. And this is what we have a patient. So we can get whatever we can from the different access points. So you can have the bedside physiological monitor, you can have the lab specimens, mechanical ventilation, infusion pump, medical applications, any other thing that you can get into integrating these signs and signals from from different inputs. So it's very important for us to have, again, an integrative approach, and this can only be achieved through interoperability and connectivity. So for that, for example, we are starting what we call a teleneonatology, which is a pilot trial where it has a patient diagnosed with BPD who are discharged home on oxygen and pulse oximeter, and we follow them in our BPD clinic. It is for 1 year, a number of patients is 20. And the important aspect here is not just virtual care platform, but we are also looking into remote real-time patient monitoring. So it is a combination of these, and the aim is to reduce readmission rate and ER visits and improve parental compliance and satisfaction. So you can see here that you will have the patient home. That information will come to our system. It will be integrated in our data, and then we can analyze it. One is to see what's happening in real time so we can make a decision. Number two, will record that data for the future and analyze it and come up with algorithms trying to have a better predictive models. So we have continuous measuring kits. It will come to the patient or us, and we have a clinician dashboard that we can make decision-making out of us. And this is how it will look like. For the level 2, which is the predictive analytics, we're having 4 different projects so far. One of them is how to predict successful extubation in BPD patients. Number 2 is pressure injury prediction. The number 3 is prediction of hospital readmission among BPD patients. And number 4 is ROP prediction. So this is the trying to predict successful extubation in BPD patients. Right now, we have a unit where it is dedicated to BPD patients. We have 24 beds, and all of these patients come to us at 36 weeks. So we start with the patients at 36 weeks who are intubated, and we're trying to find if we can predict their successful extubation. As you can see in here, our area under the curve is only 0.6. We have not been satisfied with the model yet. We're not going to go into the details of the model. We are trying to use different modeling, including Gen AI technology right now, because as I said, we were not much better than chance in predicting the patients who are going to be extubated. However, we are hopefully soon you are going to read about it in one of the journals. We have a pressure injury prediction model. Here we looked at our patients. We looked at different devices. So that was the cause of pressure injury category. We looked at all our units. We have 7 different hospitals with 10 different units. We analyze which are the most common and where they are occurring. And then we came up with different risk factors that included history and then different variables from different devices. We came up with different models like device-only device and device timing only. And ultimately, we came up with a good model. And the idea is to predict which patient is at high risk of having pressure injury within the coming 3 days. And then if we can have that, we can watch carefully, and we may need to adjust our clinical management just to prevent the injury. So far, we came up with the model, and now, as we said, we're going to start testing it in the background for the coming 3 months because we want to see it in unseen data. We had 80% or 0.8 under the area, which was pretty good, and we are going to see how the model performs in real life. We try to have a socially determined approach to predict the BPD readmissions. So we have, again, the 24-bed unit. They go home, and what we have is 6-month readmission, 47.8%, and many of them end up being in the ICU. And for that, we're trying to figure out what can predict those readmissions. And the concept in here is what we call geolocation. I don't have to go much into the details of what we use, but again, here we use a lasso regression model, which is a logistic regression. It's not much different, but than usual logistic regression, but it has its own adjustments for the machine learning. And we looked at what's called the COI, which is 29 indicators across education, health, environment, and economy. We included zip codes and all of that stuff, but what we could tell also with a good prediction is we have of 0.79. We found that actually the COI was the most predictive at 3.8, which was the highest in our model. So we're trying now to identify where these patients are located and identify what is causing the exact problem so we can focus our resources on those patient population and locations to prevent the readmission into the PICU floor or visits to the ED. We are looking into ROP development and progression. The predictive model, we are collecting data right now. We started testing, but we do not have yet specific data to share. So the level 3 is we are working on what we call intelligent dashboard. We started with the pilot project that's about breast milk at discharge. That specific dashboard, it has to be a good discovery tool. Again, real-time data or near real-time data is very important to get. Multiple data sources that includes the EMR and CHNC data and other data sets. It has to be customizable visualization, easy data analysis, make decisions fast, find solutions proactively, create reports, dashboards, and charts, and integrate advanced analytics. So this is the way it looks. So if you are a clinical provider and this is your patient, or if you are a QI directory, what you can see, this is from 2016 to 2024, and then includes all our patients from the 10 different units. And you can see we can tell, and the information will be updated every day. You can see that the ones who got breast milk versus the one who did not. Now, again, the idea is not to get just that information. We know that patients that mothers do not provide breast milk in the first 7 days are at high risk for not being discharged on breast milk. That's why we have these coded every day between green, yellow, and red. Green, that means we have breast milk. Yellow, that we do not, and or at least in the first 3 to 5 days, and then the red between the last 5 to 7 days. And our lactation specialist and our physician and our pharmacist are going to be reviewing these every day and make sure that the idea is, again, to anticipate who is going to be at high risk so we can intervene. Remember that we talked about being preventative, and this is where we're trying. So it is not being late or just having data for the sake of data. We want to intervene early so we can improve the outcomes. We started the dashboard. We are pleased so far with the results, and we are hoping to present some information in the CHNC meeting. So also you can see here that we can divide them by year and by race. And you can see that they change from 1 year to another. And again, the focus is on which population. Is it communication? Is it talking the language? Is it transportation? So these are the focus and how we can improve it for each population. Again, this data can be downloaded every day. So if you want to use machine learning or any kind of research, you don't have to ask for this data to be provided to you. This data will be updated every day, and it will be for everybody who wants to do it for any research or QI project. It will be downloaded as a CSV file pretty easily for analysis. However, what we are looking is to, again, integrate machine learning in that. So if you have any kind of set of skills in that, but it's not going to be really necessary to have high skills, just the basics of it, you should be able to use machine learning to analyze that information. We're going to expand to other metrics, including QI, clinical operation, DEI, and research, and we'll collaborate with other divisions. And this is our goal, is to have all of these metrics from, for example, breast milk at discharge, safe sleep, collapse, nosocomial infection, unplanned extubation, pressure injury. We're already working on that. We're starting now, for example, for neck, how to reduce BPD. So all of these, so we have more than 20 to 25 metrics that we are hoping to implement in the coming year. And I think with technology, we'll be able to monitor them without having the need for higher resources. So what are the opportunities and challenges? As we, before we started this talk, we started a group for what we call NeoMind AI, which is a group of neonatologists that we are expanding, and we are hoping that anybody who is interested in joining us, you can find us on LinkedIn, and we have educational meetings every month, and if you have a presentation or you would like to learn, you're most welcome to join. You can just send us a message on LinkedIn, and we'll be happy to have you join us. So of our group, we published this one a couple of months ago, which was Transforming Neonatal Care with Artificial Intelligence, Challenges, Ethical Consideration, and Opportunities. So what we talked about here are the problems. Definitely, we talk about data collection, data processing, data storage, and data analysis. So you can see really the focus is really on data, because without data, you cannot have appropriate and enough, whatever your algorithms are going to be are not going to be appropriate. So you can see, for example, you can have unbalanced over or under representation of some of your population, or you can have incomplete data. You can have improper labeling, you can have lack of governance, or you can have inconsistent practices across NICUs. So all of these, for example, harmonizing multi-center protocols, even though we can connect, for example, with other units, unless we have data which is harmonized, really we cannot use that data. Then we have institutional data silos. Data can be in different places. How we can connect them is extremely important, and how you can access it. And this is where data democratization comes into role, and how you can have self-service is very important. And then you can have bias in algorithms, errors and noise, poor data aggregation, and irrelevant data. Data availability is very important. So this is, again, these were the problems, but these are the solutions. So for example, the OMAP Common Data Model is an important platform. It is open community. It is designed to standardize and solve most of these problems. And there is the Atlas OMAP that it is for free, that you can, if your institution has access to it. There is other collaboration between healthcare and industry. For example, TriNetX is one of them. If your institution is part of that, you will be sharing your data, and you can have access to thousands and thousands of information in there. The NIH has launched the Bridge to AI program in the last 2 years. And lately, they started what's called the Chorus Network, and many of your organizations can be part of that. And the aim is really to provide a platform that connects different pieces of information. It will connect, it has the common data model for the EMR. It will have the imaging standard, and it will collect the waveform database. So hopefully in the coming year or two, we will be able to have a platform that can be shareable, so you can have much more information that you can use and test. Because the less data, the less adequate the AI outcomes. So you can see here, with another problem would be transparency and interpretability. You can see the less, so here, if you're having poor interpretable area data, for example, if you're having a model, and here it is higher interpretable. So for example, if you use linear regression, the performance is not that great in machine learning, but it is easily interpretable because you know what are the variables that were in that model. And as you can see, as you go to the right here on the x-axis, the neural networks have the highest performance, but they are not as interpretable. Neural networks and deep learning, they are definitely the highest performance, but you don't know what's going on. So that's why it's important whenever we are publishing research, and it's becoming a requirement, is to make sure that the model is transparent beside being and interpretable, so you can know exactly what's going in that model. Bias is very important. So this one here, they looked into the systematic review of bias. They looked into 987 studies that were identified. They screened 226, ended up reviewing 106. You may not be able to see this one, but they looked at the tool. I will show you in a second, but you can see just these are the studies in here. They have 4 components, and this is the overall. So green is good, yellow is not that good, red is definitely not good. So you can see that the majority are in the yellow, very few are green, and few are red. So what are these components that we talked about? Patient selection, index test, reference standard, and flow and timing, and this was the overall. So you can see that some were red of the overall, the vast majority were yellow, and the overall risk for bias for green was not more than 30%. So you can see that more than 30%, more than 60% or so are going to have some element of bias, with around 7 to 8% are completely biased, and you really cannot use that data. So that's why bias is extremely important whenever you're analyzing this information. So what we suggested in there is how you look, and we said that you need to have governance and oversight, including continuous risk reviews, monitoring adherence to principles, ethics advisory board, external auditing, and version tracking. And we looked into different elements, three main components for testability, usability, and safety, transparency and interpretability, and bias and equity fairness. And we suggested how you can look into that. But definitely ethical considerations are important whenever we are doing, and we should be having these considerations at the start of any project before we started, not at the end, because it becomes almost impossible to guarantee that we're going to have unbiased and appropriately ethical algorithm. So whenever we're looking into it, we have to start from the stage. Is extremely important. Start very early. You have to have beneficence and fidelity in your design, fairness in your evaluation, safety, accountability, and transparency in your validation, autonomy, justice, education, and implementation, justice, accountability, and vigilance in monitoring. So in healthcare, you can see that AI can be implemented everywhere, from rare diseases, diagnostics, and treatment, virtual nursing assistance, fraud, cybersecurity, gene editing. Really, it is everywhere. In neonatology, really, we are still focused on predictive analytics, but hopefully that is expanding. So, and then came the general AI, as you can see in here, that's kind of the future. So the take-home message is AI is here to stay, but you have to be realistic. Remember the winter that we went through, we do not want to get that, so do not overpromise so you underperform. It is not rocket science. You can do it. You can do it by yourself. It takes a village. You cannot do it by yourself. It takes a village. Data is extremely important, but each data point tells a story. After all, it's not about algorithms. It's about humans, so be responsible. Feel free to reach out, and either personal or to NeoMind. We are going to be very happy to welcome you for any of our meetings. And if you have any presentation, we are also happy to share either data or ideas. I hope I did not take too much of your time, the right amount of time.
Thank you, Dr. Ferzli. That was a really great presentation. We'll take any questions that anybody has. I don't think I see any in the chat right now, but please feel free to put any questions. And then I'll also put a survey in regards to today's presentation in the chat. I have a question, Dr. Ferzli, if that's okay.
Of course.
I think something that's hot right now in neonatology as well is POCUS, or point of care ultrasound. What do
Yes.
you believe is AI's role in POCUS as it becomes more of a staple in the unit?
Yeah, I think it's a very good question, because the really what's important is how you can integrate any piece of information, and hopefully in real time. So now we have, between the CNNs and what the Gen AI can do, we can analyze all of that information integrated into any model. And that's why we are looking into any kind of imaging would be huge. So for example, if the more information you have, the best your outcome is in algorithm development. And this is what we are having a problem. So whenever we're looking to our BPD component here in the project we're doing, we are a little bit short on number of patients, although we have 12 years, but we are looking at severe BPD in this case. So you don't have as many of those, and most of them come to us intubated. So data integration and data sharing is going to be extremely important. For that, when you're having this focus, just think about it, for example, is you have that ultrasound. Let's say you're looking for cardiac output, and you have your heart rate monitoring. And if you can integrate that information together, you might be able to come up with the predictive. Uh, uh, I would say you have to have, first of all, you have to get the data in there, right? But once you have that data, and so you will have probably an algorithm that says when you do your ultrasound and your cardiac output, I don't know, is 50%, and you're having this kind of rhythm on your EKG, and your blood pressure is so and so, you may not be able to think about it yourself and put them together, but your machine will ultimately come and tell you the risk of this patient going into shock probably will become, I know, 80%. So you start working into that. So this would be one way of looking at it. I think that, where the real time is going to be very helpful. But again, the idea is to gather that information and be able to analyze it. And it's not going to be simple because, again, as I said, the number of data points is going to be extremely important. And then being generalizable is extremely another important problem, because what I can come up as a model may not apply to your institution. And I think that's part of it. That can become an issue for institutions that do not have the ability of doing their own algorithms. Now, if you go for a third-party vendor, they have their own algorithms, but most of the time, really, you cannot just take it out of the box and say, I'm going to use it. Every time somebody used it, the outcomes was not really good. So how to make these algorithms generalizable is going to be really decided on how much data we can use. And the data has to be harmonized, because even our data, when we change the ventilators, we could not use before and after different kind of ventilator. So these are extremely important pitfalls that we have to think of them all the time. But what you said, I think this is one of the future things that can be helpful using POCUS.
Thank you. There's another question in the chat. Somebody has a question about the model that you had for extubation BPD patients. You mentioned earlier that the model is not performing as well as you would like at this time. Are you working to improve it currently?
Yes, so there have been new publications using different methods. We tried to use the usual time series methods to analyze our the EKG, the vital signs between EKG and saturation, but we did not find much difference to be able to. What we have is the population is very homogeneous, because we try to extubate them really when they are very similar to each other, and the number is not that great. So probably we have around 100 extubations that happened over the last 10 years. So that makes it a little bit hard. But now when new methods came out, so we started last week. I spent probably a week trying to figure it out. So our data scientist is going to work over the coming week trying to figure out if we can improve that, and I'm hoping we can. So I'm trying to increase the size of our how we can, because now we looked for, let's say, as one data set, like one day before extubation or 6 hours or so. We're trying to make them into smaller segments and use, again, different techniques. One of them would be using Gen AI for analysis.
Are there any other questions for Dr. Ferzli at this time? Well, I would like to remind everybody again to fill out the red cap survey that I popped into the chat a few moments ago, and to also thank our presenter today for such a exciting discussion on AI in the NICU. Thank you.
Thank you.